This module is going to be all about gas laws. So let's take a look at this here. Gas laws, you can find the information in your e-textbook on chapter 13 if some of this doesn't make sense. But I'm just going to go through some basic things here and then really work through in a series of videos, very short videos, examples of the different gas laws. But before we get started with the gas laws, let's talk about describing gases. So one of the first things we want to talk about here is, how do we describe a gas sample? You think of something like a balloon, but gases, atmospheric gas is all around us. It's made up of a lot of nitrogen and oxygen. But if we look at a gas sample, one of the things we could say, or three of the things we could say is typically gases are going to be described as high energy particles. They're going to tend to, because they're high energy, they're going to want to spread apart. And they spread apart because they're moving at very high velocities. So again, if you're watching this video, it'd be good to take some notes, just real basics here, and follow along with me. So writing these things down would be good. What quantities look at the next question here, what quantities can we measure? So if we're using gas, it's kind of hard to look at a gas sample and understand it because typically it's invisible. But we can do a few things, like for example, we can measure the volume. We can measure the volume of a gas, we can measure the pressure, and we can measure temperature and density. And these are actually going to be things we're going to look at a lot. You might think of measuring the pressure of a tire. Maybe you've, in spring here, when you're ready to get on your bike and you pull your bike out of the garage and the tire is flat. So you hopefully can figure out how to get your hands on something that could blow up your bike tire, and one of the things you want to read is the pressure on the side of the tire, usually like 45 to 60 pounds. But temperature and volume are going to be things that are directly going to affect pressure. So we'll look at that soon too, and then density also. So if you kind of look at this down here, this is sort of an interesting idea because on top of us right now is miles and miles of gases. And because they do have masses, very slight masses, they actually pull down directly on top of us because of the gravity of Earth. And because of that, there's a pressure that exists that's on Earth, and an atmospheric pressure. And so if we fill in these blanks here, the weight, which is a force, the weight of air from the surrounding atmosphere, again, lots of atmospheric gases in the atmosphere, nitrogen, oxygen, carbon dioxide, causes atmospheric pressure to be felt on the Earth's surface, which is where we're at. So if you look at all these different, you can see the miles of different layers of atmosphere that you learned in middle school, and how right on top of it, it's a 1 square inch is what this says right here. So just 1 square inch it's all coming down directly. Gravity is pulling down on it. It's sort of like if you think about if you're going on a trip and you're going maybe through the hills of Tennessee on your way to Florida, and here you are in your car, and right here there is going to be more of this gas, atmospheric gas, pulling down. Gravity's pulling down on Earth equally everywhere. And so when you go up the hill here in your car, then you're going to have a lot less. So you'll notice sometimes, whether you're in a car or an airplane, in an airplane you're doing the same thing. You're going up, you're reducing the amount of atmospheric gas on top of your head. You'll notice that your ears will pop. And why are your ears popping? And that has to do with the fact that the pressure inside of your head is constant, but when the pressure on top of your head changes, then somehow your body needs to sort of recalibrate for that. Likewise, if you, let's say, we're going to go underwater, it would be even worse, because you'd have the weight of the atmospheric gas plus the weight of water on top of you. So that's why you can't just do a deep dive. You might notice, like, if you jump off a high dive in a pond, when you hit the bottom and you go deep, not only does it get cold, but it also, you might have some sort of like sore ear, or notice that your ear is popping. Going into this, how do we measure atmospheric pressure? One of the first ideas was, let's come up with some sort of contraption. And Torricelli, an Italian scientist in the 1640s, started sort of messing around with this idea, and it's on the right here if you kind of look at it. And he looked at the fact that we could take mercury, which we don't play around with today because we know it's toxic. But he took some mercury, and as you can see here, he put mercury into this sort of pan, and then he filled the tube with mercury, and then he put it upright, so pretty much turned it upside down. And what happened was, there was this space right here, and you can see up here where his hand is that same space. And so what happened is, he noticed he could sort of check this from time to time. And the weather, depending on what sort of weather was going on outside, this would move, this mercury that's inside of here would move up and down. And so we have high pressure and low pressure. So that's sort of what, when you watch the news report, which I don't, I usually just look at my weather app, but maybe you've heard somebody say, we have a high pressure system, and high pressure typically means nice weather, whereas low pressure is going to mean some sort of bad weather, whether it be some snowstorm or thunderstorm, or worse yet, a tornado. So what he found was, we can use what's going on is the atmospheric pressure would push down on this pan right here, which there's nowhere else for the mercury to go. It would then go up. So as it went up, this gap would get smaller, and he'd have these millimeters of Hg, so millimeters of mercury. And so however many millimeters this went up, that would tell you a rise in the mercury. So the mercury raised, so that means that you have high pressure. And then as less pressure pushes down here, this would actually drop down, and we'd have low pressure. So anyway, this is just sort of an idea that came. A manometer is what we call it, or excuse me, a barometer is what we have here with Torricelli. And he found that 760 millimeters of mercury was going to be normal atmospheric pressure. And what is normal? Well, kind of everyday, average, fair weather sort of thing. So let's take a look here. Excuse me, I shouldn't have wrote in there. So anyway, the weight of the air pressure going down, if you didn't catch what I was saying there, here are some key points we can get. Okay, so I got rid of my markers there. So the weight of the air, kind of summarizing what I just tried to say there, the weight of the air is pressing down on the mercury, of course. So then the mercury had to go up the column, and then the greater the pressure, the farther the mercury rises. So just kind of capturing it there, so if you want some bullet points to write down. The problem is with pressure, it's not a problem. The problem is we talked about this at the beginning of the year with SI system, the International System of Units, and how a mile doesn't really make sense, but really a kilometer does, because it's 1,000 meters and the prefixes and all that. So you can see here, this is ridiculous. Look, we got 1, 2, 3, 4, 5, 6 different units for pressure. So a lot of these have a lot of different crazy origins. Not really crazy, but unexpected. The one right here is expected, TORS. That's named after Torricelli. And then this one actually makes the most sense, kind of, sort of, because it's millimeters of mercury. But then the idea of pascals came. Basically, a lot of men with last names, Pascal, Torricelli. That's the kilopascals, which sort of makes sense. In the English version, we got to get our pounds per square inch and our inches of mercury. So all of these kind of came to be as far as here's some great here's some different units we can use. And like I said, your bike tire uses PSI. That's what it says on the side of the tube. Probably, though, the one that makes this most sense as far as the one that we use in the International System of Units is the atmosphere. And the atmosphere, it makes sense because it's just, and by the way, all these are standard averages. So like what it is at STP, and we'll talk about that in a second. So like on your average day, what's the pressure going to be? It's going to be all these numbers, which essentially equal the same thing. So 1 atmosphere equals all of these numbers that you see. And so we use atmospheres as being the basis for the SI because it makes sense. 1 is the most average. So what we end up doing every once in a while, though, is we run into all of these different units constantly. So because of that, you need to be pretty good at unit conversions. And this is really easy stuff. So what we'll do here, so this is pretty easy stuff. So for example, right here, if we, example 1, if we have 3.2 atmospheres, how would we convert that to PSIs? Well, we'd simply do a unit conversion. And you can see here that I took what I was given, 3.2 atmospheres, and then I set up a unit conversion. And I got, how did I get these numbers? Well, first of all, I got 1 atmosphere. I put that on bottom because I want to cancel out the atmospheres. And then I took 14.7 psi and I put it on the numerator. Simply multiply that, and of course, then my atmospheres cancel out, and I'm left with 47 psi. Of course, I'd want to use my sig figs. Example on the left here, or on the right, excuse me, we're going to take 600 millimeters of mercury, and I'm going to look up here and I'm going to say, okay, I know all of these things up here. I'm just going to take my numbers. I'm going to take 760 millimeters of mercury, put that in the bottom, and then I'm going to put 101.325 kilopascals, put it on top. I'm going to multiply the numerators and divide by the denominator to get a very clean answer of 80.0 kilopascals. So those are 2 examples. I don't think you need more than 2. And what I'm going to do now is the next thing in the module is an assignment that just lets you practice these things. And don't worry, this thing up here will be at the top of that. You can use it. It's not going to take you very long. Make sure you use your sig figs, and you don't need to put the units in. Just put the number into that Canvas quiz. So do that and check it out, and then the next video will be on the very next gas law. So we'll check that out and keep moving through this module.